Okay, all right. I think Serena's got us recording now. So yeah, it's a pleasure to introduce Marcelo Barraza Alfaro. Marcelo is doing, I guess, what a lot of people, especially from Europe, do. People who are doing good work and have good advisors, like Marcelo obviously has. They send them on a tour of U.S. institutions, and so Marcelo is joining us on a tour. I think you began in California and you've gradually been making your way east. I think it's going to finish up or, eventually, visit, I believe, the CCA and places like that. But it's a real pleasure to have him here today. So before this trip, some of Marcelo's origin story is that he did an undergraduate degree and a master's degree at the University of Chile, working with Simon Casasas, if I'm saying that correctly. And then the work he's doing now is obviously somewhat related to that work on disks. He's now almost completed his PhD, working primarily with Mario Flock. I see some other collaborators here on a very exciting current topic in disks, the vertical shear instability. And while this isn't a lot of theorists are interested in this, what's really exciting about Marcelo's work is that he's making connections to the observed properties of protoplanetary disks. So without any further ado, I'll let Marcelo take it away.
Okay. Hi, everyone. First of all, thank you to Andrew for giving me the chance to speak today here in the seminar. I will talk a little bit about my PhD work, which is studying the kinematical signatures that are produced by the vertical shear instability, which is purely hydrodynamical instability. The importance of this instability comes from that it could produce some level of gas turbulence in the outer regions of protoplanetary disks. And this work was in collaboration with, of course, my advisor, Mario Flock, and Sebastian Marino, which is now at Cambridge, the University of Cambridge, and Sebastian Perez, which is now working at the University of Santiago in Chile. So to start, I will give a brief outline of my talk. I will start talking a little bit about planet-forming disks for those who are not familiar with it, and then why it's important to study gas turbulence in disks. Continuing with the vertical shear instability, then jump into how people observe gas kinematic and what techniques are used to explore the kinematics of disks, and finishing with my methods and results and some takeaway messages. So first of all, for those who are not familiar with disks, but I think most of the audience is familiar with disks, but anyways, well, the disk is, the planet-forming disk is a circumstellar disk made of gas and dust, which is a byproduct of the star formation process. So you have material of the molecular cloud where the star forms by gravity and angular momentum conservation, you form a circumstellar disk. And it's from this material that, or inside this disk, where planets can form and feed from the material of the circumstellar disk. And for example, can carve gaps in the disk. When later on, when the gas of the disk is dispersed, you end up with a formed planetary system, which could also have rings of debris that have been observed in other exoplanetary systems. So the hydrodynamical instabilities that I am talking about is important mostly when the disk is already formed and is stable to the gravitational instabilities. And until it can also be active when having planets embedded in the disk, but it's important as long as the disk has an important amount of gas. For debris disk might not be might not be relevant. So to understand the evolution of this protoplanetary disk or planet-forming disk, it has been people have done surveys of protoplanetary disk and trying to observe what kind of substructures they have, or if they have substructures, and also if there are some pathways towards understanding the evolution of protoplanetary disks. And the main results, for example, from this particular survey, that is the D-sharp ALMA large program, is that in the dust continuum, which is what is observed in this panel at millimeter wavelength, substructures are present in all the sample. So all the disks show some amount of substructure. And the most common one are rings or rings and gaps that are axisymmetric. Now there are some problems to explain these rings from the theoretical side, as there are many different mechanisms that can produce rings, right? So from the dust continuum alone, it's hard to say which process is carving this or forming these substructures. So that's where gas is important, because all these structures in the dust are produced by aerodynamical drag from the movement of the gas. So the mechanisms that are producing rings are actually modifying the gas velocities or the pressure gradient of the disk in the gas, which leads to the formation of dust rings. So in the recent years, more effort has been put into observing gas in high resolution. And for example, in these results of the recently published ALMA MAPS program, you see 5 disks in the integrated emission of 12 CO2 to 1. And in the lower row, you see the same disks, but in dust continuum. And there are already some substructures that can be also observed in the gas, which in this case will be more related to temperature variations in the disk. Now the good thing is that with these observations, we can also study the gas kinematics and prove more in detail what's the movement of the gas in the disk, which I am going to talk about later. But my point is that studying the gas is quite important to understand the origin of substructures in protoplanetary disks. And also to know, we have a lot of information in the gas observations about the disk conditions. For example, the temperature of the disk. And one of the most important properties of the gas is the turbulence of the gas. And in the main importance of gas turbulence in disk is that enhances the transport of angular momentum through the disk, and also heat. And it can create this, for example, here I show an example of a turbulent flow, which is the atmosphere of Jupiter, observed by Juno. And you have, when you have a turbulent fluid, you see a lot of a lot of structures in the disk. For example, vortices or eddies of different sizes. So this the gas turbulence is actually quite relevant in all the processes that are related to planet formation. For example, it can contribute to disk accretion by transporting angular momentum outwards through the disk. It can affect dust evolution. Use one example, how the dust is settling towards the midplane of the disk. It can affect planetesimal formation. For example, if you some mechanisms that trigger turbulence can produce enhancement of the dust to gas mass ratio in some regions of the disk, like localized increase of the dust to gas mass ratio. And this can help to trigger planetesimal formation via the streaming instability. It can affect how substructure evolve and form in disks. For example, if you have a transition in the turbulence level of the disk, for example at the edge of the so-called MRI dead zone, you can create substructures. It can also affect planet-disk interactions, for example, in how the planet carves a gap, that when the level of turbulence is lower in the disk, a planet can create, of the same mass, can create a deeper gap in the disk, or even if it's very, very low, it can actually produce multiple gaps, for example. And the turbulence level can also affect the planet migration. And finally, it can also affect the disk chemistry by mixing up everything in the disk. So, I mean, the turbulence level of the gas is quite important in all these processes, and it has been studied that is important. But in most of the studies, they simplify the turbulence using the very famous alpha prescription from the 70s, where you assume a constant alpha that you can vary in your different models and study how the turbulence affects the process that you are interested about. But the thing is that at this point, I think we really need to understand all these processes with a more realistic turbulence. For example, including, or in other words, including running like hydro simulations with hydrodynamical instabilities or MRI instabilities, and study how these affect these different processes. However, this is kind of expensive, and also we don't know what kind of process is dominating a source of turbulence in the different region of the disk, and this is a problem. Because you can have that in different regions of the disk, you have different source of turbulence. For example, here in this very simplified picture of a protoplanetary disk, in the more outer layers of a disk, let's say, you will have that the gas is highly ionized. And in this case, the magnetorotational instability can operate and it can dominate a source of turbulence. However, in the deeper layers of the disk, where the gas is weakly ionized, you can also have non-ideal MHD terms that can suppress the magnetorotational instability and create this so-called dead zone, where you don't have the MRI operating. And inside this region, you can have that the purely hydrodynamical instabilities can operate and dominate a source of turbulence. However, this can be quite complicated again, because inside the MRI dead zone, you can have different hydrodynamical instabilities operating. So, for example, here I show 4 complicated names of hydrodynamical instabilities, but the main point from this figure, for example, is that where each hydrodynamical instability operates depends strongly on the local cooling timescale of the disk. And for example, the zombie vortex instability works in the regions where you have slow cooling, and the vertical shear instability works in the regions where you have very fast cooling.
So Marcelo, sorry to interrupt, but I think it's a pretty important clarification point that these aren't the regions where these instabilities will operate, it's regions where they might operate.
Yeah,
because it's not just a cooling time requirement. There are requirements on entropy gradients and other things which are in many cases unlikely or unproven to exist in general.
Yes, that's an important point.
Yeah, and the radius, is it dependence? It depends on the stellar gas, and right.
Oh, sure. And of course, this will depend on details of opacities and everything.
Yes. But that's and also these regions can overlap with each other. So what I want to show from this figure is that the vertical shear instability in this particular model, of course, which is for a solar mass star, will operate from tens to hundreds of AU. And this is the region where you can observe the disk and resolve the disk with the ALMA interferometer. So in a very simplified picture, again, you might have these many different regions in the disks where you have different source of turbulence from different mechanisms. And we need some more work to understand if these regions actually, these instabilities are actually operating in these regions and where are operating. And this will be more from the observational side, I would say. And this is a more realistic picture where they map where the different instabilities operate, and you again have some overlapping of the different instabilities. For example, here, and you again have the VSI working in the outer regions of the disk. Now about the vertical shear instability, it needs quite simple, quite easy conditions to operate. First, you need the vertical shear, of course, that comes naturally from having a radial entropy and temperature gradients. And you need also fast cooling, because otherwise buoyancy forces stabilize the disk against the VSI. And in this figure, I show a 2D plot of the vertical height versus radius. And the color, in grayscale, is the vertical velocity of the gas. And what you see first is the linear growth of the instability with the so-called finger modes in the surface of the disk. And in the last figure, here you see the saturated state of the instability, where you have these columns of gas moving up and down through the disk. Now coming back to why it's important to study these instabilities for the different processes important for planet formation. Here I want to highlight 3 works. For example, that the VSI can affect the dust evolution by mixing up grains and lifting up grains from the midplane to the surface of the disk or higher up in the disk, and increase the dust pressure or dust scale height. It can also produce structures. For example, in the work by Natasha Manger, the VSI can trigger also the Rossby wave instability and create large-scale vortices, which might trap dust and give good conditions for the dust to grow. And finally, from Schaefer, the work from Schaefer, that these flows produced by the gas flows produced by the VSI create traffic jams in the dust, and these traffic jams can increase the local dust to gas mass ratio and can help to trigger the streaming instability. Now jumping to the CO kinematic observations. Well, this is actually quite new, and thanks to ALMA, I think it's used like about 4 years that people have been observing a disk with ALMA, studying the velocities of the gas in detail. And here you have one of the most studied disks. I think it's HD 163296. And you have here the different individual velocity channels of emission, giving this typical butterfly pattern of an inclined disk. And you can actually see the 2 emission layers of this with this high resolution. And this is the integrated intensity of the disk. Now the amazing thing is that these observations are so good that you can actually resolve perturbations from the expected Keplerian pattern of a disk in equilibrium or slightly sub-Keplerian pattern. And this is one example that in an individual channel, they detected some deviation from what you expect of as an unperturbed disk, which will be like this. And this was proposed to be evidence of embedded planet perturbing the velocities of the gas around the planet, producing this, like they call it, a kink. But there is another way to study the structures produced like perturbations in the disk, which is to study the line of sight velocity map or moment one map or line centroid map, depending on the method you use, which is basically measure the Doppler shift of the line at each pixel. And then you, for example, here you have a smooth Keplerian disk rotating clockwise, and you will see the red shift and blue shift of the line. Now what you can do to extract perturbations is to fit a model like this to your data, assuming, for example, a Keplerian rotation, some prescription for the radial profile of the velocity, and a good constraint to your systemic velocity. And you can fit for the emission surface of the disk or the stellar mass, for example, and get the best model that can fit your data in the line centroid map. Then if you subtract this smooth model in the residuals, you will see the non-Keplerian features will be perturbations in the gas velocity. And this is one example that is TW Hydra, one of the best observations so far of this in gas kinematics. And in the left, you have the velocity centroid map. And in the right, you have the residuals from subtracting the best Keplerian model to the data. And what you obtain are these spirals of gas moving up and down through the disk because it's almost face on. And this can be explained, for example, by having a planet and that is producing spirals via the buoyancy resonances, which was one mechanism proposed by Jahan Bai. So this shows the incredible potential of ALMA to extract perturbations in the disk, and this can be used to, for example, understand what's the origin behind the substructures that we see in the dust. So these results trigger a lot of work trying to explore what kind of kinematical signatures will be produced for the different mechanisms. And here I have a short list of a few. For example, embedded planets, flybys, gravitational instabilities, and large-scale vortices. That this is a small, like what kind of signatures they produce. For example, a massive planet of above a few Jupiter masses, like this is a 10 Jupiter mass planet, will create a localized deviation in the gas velocities and also trigger spiral arms. You can also observe some spiral arms produced by a substellar flyby or a stellar flyby. And from gravitational instabilities, if the disk is very massive, you create a large-scale spiral arms that can trigger these wiggles in the residuals when subtracting a Keplerian model. And finally, you have here the residuals of a large-scale vortex produced at the edge of a cavity in a disk, which they predict that it can produce a signature of about 50 meters per second in the residuals. So now to my work, we continue this trend, and we wanted to study if we could actually observe some signatures in the kinematics of the vertical shear instability, which, as I mentioned before, is predicted to work between the tens to hundreds of AU, which is the region which ALMA observes in higher resolution, or is ALMA observes the best. What kind of signatures are produced by the VSI in the channel maps alone, in the single channel maps, and also in the residuals of the velocity centering maps? And finally, if these are observable with the ALMA interferometer. So we started with 3D hydro simulations using the Pluto code in a global simulation in spherical coordinates using the model of Richard Nelson. These simulations are inviscid and locally isothermal. So in our simulation, you have very strong VSI. Then the outputs of the simulations, the gas density and the velocity field, we put as input into RIMC3D, the radiative transfer code. We assume a dust structure because we don't simulate the dust, and we compute the dust thermal temperature, the temperature of the dust via thermal Monte Carlo. And assuming that the dust has the same temperature as the gas, we compute a gas line emission data cubes for 12CO, 13CO, and C18O in the 2-to-1 transition. Like the raw synthetic data cubes we put through CASA SimObserve, and we include a realistic like noise, and also we clean the image to produce simulated ALMA observations. And from the simulated ALMA observations, we compute the observables, which will be the velocity centering maps that I mentioned before with the package veteran moments, and the deviations from Keplerian rotation by fitting a model using the Python package ID. Both Python packages are written by Richard T. So this is a 3D figure or rendering of the simulation that we post-processed, showing the magnitude of the velocity perturbation. in the units of sound speed. And what I want to highlight from this figure is that the perturbations first are weaker towards the midplane and are more axisymmetric towards the midplane. But in the surface, they have a stronger magnitudes and they look more turbulent. If we decompose these velocities into the different components, we have that first, in the first column is the gas density, the perturbations in the gas density. In the second column is the radial velocity of the gas. Then the third column is the gas velocity in the vertical direction or meridional velocity. And finally, we have the azimuthal deviations from Keplerian rotation. And what I want to sorry, again. The first row is at the midplane of the disk. And the second row is above 3 pressure scale height of the disk. And this one is a vertical cut. So what I want to highlight here is that the radial and azimuthal deviations are stronger closer to the surface of the disk and really weak at the midplane. However, the meridional velocity is strong both at the surface and the midplane of the disk because you have this whole column of gas from the VSI. Also, the meridional velocity perturbations are quite axisymmetric. So then we put all this information into REMC 3D and we explore what kind of signatures do we get on the magnitudes. And for example, this is 4 individual channels for 3 different disk inclinations. And what we can see is already that the VSI produces some observable features, but are really weaker or difficult to see for the high inclination case, which are seen as spurs or little wiggles in the surface. And they are present in all the channel maps. This is expected as the perturbations from the VSI are in the whole disk and are not localized. But something interesting is that it's stronger for or are more prominent for the low inclination case or almost face on disk. Now, if we go to the line centering maps, in the left column, you see the velocity centering maps for 3 different disk inclinations. And the second column is the expected residual from subtracting a perfect model. So this is done by subtracting a second radio transfer model, which is a disk following a Keplerian rotation. And then we compute 2 different velocity centering maps and subtract them. And what you get is that you will expect to see these kind of rings of gas velocities moving up and down when you have the almost face on disk. And as you increase inclination, they become more like arc features in the residuals. And these have magnitudes of about 60 meters per second. In the last column, what you see is the residuals from subtracting a Keplerian model, but this is done more in the observational way that we did the ALMA simulated observation using 1 extended and 1 compact configuration. And then using EDI, the Python package, you fit the best model to your original velocity centering map and subtract it to it. So this will be what an observer will do in the data. and you can recover very well the structures from the VSI for the 5 and 20 degrees inclination. But as you increase inclination, this becomes more difficult, and you need probably a more probably more work to fit a good model. And we want to show that for higher inclination disks, you can have it's easier to get errors, for example, in the fitting of the emission surface that create these large-scale modulations in the residuals. But you can still recover arcs of non-Keplerian motion. These simulated observations have a resolution of 50 meters per second channels and about 10 AU spatial resolution or 8 AU spatial resolution, something like that. Then we explore where these structures come from. And well, this is, each column shows the contribution to the line of sight velocity residuals from subtracting a Keplerian disk of each velocity component. So, for example, here we did the radial transfer model, considering only the radial velocity from a VSI disk and the other two from a disk in equilibrium. So you will see only the contribution of the radial velocity to the perturbations that we predict in the kinematics. And what you observe is that the structure comes mainly from the vertical velocity or meridional velocity motions that are produced by the VSI. And as you increase inclination, the radial velocity can contribute with some asymmetries in the residuals. Now, then we explore for different isotopologues of CO. And for example, from top to bottom, you increase inclination, and from left to right, you decrease abundance. So this will be tracing the layers closer to the midplane of the disk. And as you expect that from these perturbations coming from the vertical motions of the gas, which is moving, is the whole column of the disk moving up and down, you see a similar structure in the surface and closer to the midplane. The only thing is that the perturbations are weaker closer to the midplane, and also because you integrate in a longer column, all the perturbations get more diffuse or smooth. And finally, what we tested with is that, well, Jake Simon, which is now in the audience, I think, they predicted that for a simulation that you have the magnetorotation instability, which is the blue line, you will see a change in the line profile if compared to a disk with no turbulence, which is this yellowish golden line. And this can be used as a method to constrain turbulence in protoplanetary disk from unresolved observations. And we compare our VSI simulation, the line profile of VSI simulation or prediction, sorry, with a laminar disk, and we see that the difference is negligible. So we don't expect any difference in the line shape from the vertical shear instability. Particularly, this is a quite high temperature disk, but we also tested for a low temperature disk, and there is a difference, but it's very small. It's really, really small. So we don't expect to see any non-thermal broadening from the VSI if we use this approach to constrain turbulence in disks. And well, something of what I am working on for the ones that are interested is including planets in a VSI-unstable disk. And for example, in this figure from Sebastian Perez is a simulation of a planet, a Jupiter planet embedded in a disk. And you see that creates very strong perturbations, particularly in the azimuthal velocity of the gas. But it can also create some perturbations in the other two components of the velocity. And this has been explored to create non-Keplerian signatures in the gas kinematics. This will be the residuals from subtracting a Keplerian model to an ALMA simulated observation. And what I am doing now is to include a planet in a VSI-unstable disk and predict what's the change on the dynamics and how would affect the kinematic observations. And what we are observing is that, for example, it was also shown by Moritz Stoll, I think it's Stoll et al., that if you have a planet embedded in a VSI-unstable disk, you can perturb the disk in the gap region. And for example, here you have a Jupiter mass planet around this location, and you damp all the vertical motions from the VSI along the gap region. So you will only observe the VSI here far from the planet orbit, the planet's orbit. In the case of this is a Saturn mass planet, it's harder to see the difference between having an embedded Saturn mass and a disk with only VSI. And only by increasing inclination, you will see a clear difference. For example, for example, in an inclination of 35 degrees, you will see clearly a Jupiter mass planet embedded in the disk. However, if you have a Saturn mass planet, it might be difficult to disentangle between having a planet with VSI or VSI alone. So we are exploring ways to disentangle between these two scenarios. But it's clear that, for example, if you have a Jupiter mass planet, you will create this localized deviation in the velocity, in the residuals from a Keplerian disk. So they take-home messages, from our results, it's possible that studying the kinematical signatures of hydrodynamical turbulence could probe the origin of gas turbulence in protoplanetary disks. But for this, you need to combine 3D global hydro simulations and connect them with high-resolution ALMA observations, which both are expensive simulation from the computational side and also observations, and the sense that to have a good kinematic observation, you need probably like more than 6 or 7 hours of ALMA time or even more, which is quite a lot. And it's really hard to get this data. Luckily, there is a large program accepted to observe 15 protoplanetary disks in the 3 CO isotopologues and CS, which will give I think it will give a lot of information about the gas kinematics. Hopefully, we can prove more planets embedded in disk and also some physics of the disk. And the final point is that the VSI can produce observable features in the channel maps seen as spurs or wiggles in the channels, and also can create residuals from a Keplerian disk when you subtract a Keplerian model to a line centroid map, and are seen as rings for a low inclination disk, and also arcs for intermediate inclination disks. Yes, so thank you for your attention, and I will be happy to answer any questions.
Okay, so Jake.
Hi, Marcelo. Thank you for a very interesting talk. So I'm a little bit confused because you showed that the line profiles don't seem to care whether there's VSI or not, but then the channel maps did, right? And so at least in the stuff that we did with Meredith, that I did with Meredith, there was sort of a one-to-one correspondence. Like if the channel maps were broad, then we saw a change in the peak to trough ratio in terms of the line profile. Of course, the absolute value is subject to the uncertainty or the systematic uncertainty from the ALMA calibration, but I was just wondering, like, if you had a comment on that, and also if you had a comment on the fact that you do see broad channel maps and what that means compared to the fact that we actually don't observe very many disks with such broad channel maps.
Yes, that's a good question. I think that what we think it's the problem is that these perturbations are quite small. Like the broadening of the channel is actually not quite big compared to the laminar case, because I mean in this particular model the disk has a really high temperature, so the wings are, I mean the channels are broad because the disk is very hot.
Okay, I see.
But for example, we explore, and this is washed out from having a 30 AU beam size already.
Oh, okay. So this is not including the systematics and stuff that you would have, right?
So,
is that what you're saying?
I think that yeah. What I think is that these wiggles are used very small, spatially, and also in magnitude, in velocity magnitude. So I mean,
okay.
I don't know if I mean, I think this needs more exploration to see what's the limit that we start to see some VSI running, because there is some VSI running, but it's just very small, and from our models is negligible compared to the thermal broadening.
Okay.
But yeah, that's something interesting to check.
Yeah. All right. Thank you.
Thank you. So, Leonardo, is the question.
Yeah. Hi. Hi, Marcelo. Thanks. Can you hear me?
Yes.
Yeah. So I was wondering what was the time scale of the integration for the Saturn mass planet in your comparison. If was already a gap there, and are you expecting that
That's yeah.
more damping of the BSI for longer integrations is this depending on the gap properties like the depth, or can you comment a little bit more about that? Thank you.
Yes, that's a good question. This is, I think, after it's like 100 orbits of the planet. And I think in this plot, what I did was to compare the same stage of the simulation, which obviously in Saturn, the Saturn planets takes more time to create a deep gap or a steady state gap. And actually later in the simulation, you see also damping like in the Jupiter mass case. So that's something that it's the case that with the Saturn mass planet, you also expect damping from the VSI. It's just that in these predictions, it's an earlier time, which is interesting too. You need some, I think it's like 500, no, like 300 orbits of the Saturn mass planet to create where you have already the VSI along the gap region. Yeah.
So Marcelo, thanks for the talk. I think you did a great job motivating why we see the VSI has, I think, deservedly gotten the most attention of all these sort of hydrodynamic or thermodynamic instabilities. One of the sort of technical issues, at least with the simple analyses of the VSI, though, is that you get these so-called surface modes at surfaces that in the calculations are artificial. They don't represent a real disk surface, but just where your calculation ends. Now, I think some works, and you showed, I think one from Mario Flock, have gotten rid of these surface modes in what seemed like a realistic way by doing the opacities better. It looked to me like your calculations still had a lot of surface activity. So I wonder if you could comment on whether you think that affects the observational consequences and whether you think you could, I don't know, do it in these other cases where you might be able to suppress those surface modes.
Yes, that's a good point. And yeah, it's something that was worrying me. But I mean, the layer that we trace with CO is like about like one scale height from the surface of the simulation, the edge of the simulation. So we don't think that for these particular predictions are affecting the kinematics results. But if you want to explore tracers that are more into the surface or disks that have layers, like particular disks that have a CO layer upper in the disk, like 4 scale height, then we will need to increase the disk domain. About the damping, I think might be an improvement to add some damping layer in the surface or something like this to prevent artifacts closer to the surface, which if you are exploring close to that region with the kinematics might affect your prediction. In Mario's simulations, he includes radiation, so probably there is some damping from the radiation or the temperature evolution of the disk. But so far, I have asked to other people to send me some data of the VSI simulations too, to check, and they see similar dynamics. So I would say that the overall dynamics of my simulation is expected from a VSI-unstable disk, but we need some improvements if you want to explore more closer to the surface of the disk.
Yeah, no, thanks. And obviously you did show that there was a signal, right, even from the very most optically thin tracers. It seemed to persist through. I guess, I'm sorry, since no observers asked this, I'll impersonate the observers and ask what you, in modeling the observations, what you included in terms of beam size. Was there anything in terms of signal to noise and observing time? Some of these results look very good, almost too good for real ALMA observations.
Yeah, that's true.
Thanks for asking.
For these particular predictions, I mean, this is a combination of of configuration 8 and 5. And the beam is what that we get is around like 8 or 9 AU, and this particular model is at 100 parsec. So I mean, this is, of course, these detections are possible only in the most and the brightest disks that are closer to us. About the integration time for this particular model, I think we did, it was like 10 or 12 hours of integration, but I don't remember, but it was a lot. Yeah.
A large program.
Yeah, I talked to a lot of people, and they say that, I mean, we should really go to like the galaxy people and observe one disk for many hours.
Yes, you can have one disk for a long, very high sensitive, high resolution imaging. So you have to make a case for that.
Apparently, the galaxy people say that we are too shy. But I mean that the large program accepted will observe the brightest disk, some of the brightest disks, and for 9 or 8 hours each. So I think it will be good to get some tentative detections of weak perturbations, and then go for a follow-up or a more deeper observation with I don't know, maybe a longer baselines. But yeah, I mean, I would say this is really at the edge of what ALMA can observe with the current capabilities, of course. They are planning some improvements, but I think they still a few years to go.
So, if you have time, just to follow up with a little bit of discussion.
Yeah, there's one last question as well.
Oh,
yeah. Orkan had, yeah, let me go ahead first. Orkan asks at what height above the midplane are you seeing the surface smooth artifact?
I mean, it's really at a few cells from the. I would say that is not. I would not believe the result. I used a few cells from the edge of the simulations, and these are at the 4 pressure scale heights above the midplane.
And yeah, and I was just wondering, this is sort of a practical issue, and I think maybe explains some of the work you were showing at the end. But obviously, if you're studying the largest, brightest disks, those are well known to have complicated, large-scale structures, whereas it looks like you're mostly, until the stuff at the end, you're mainly considering the smooth disks. So I guess with that.
Yeah.
Part of the
that's
the work at the end.
Yeah, that's the motivation that I think there are no smooth disks like from the brightest. All of them have signatures of gaps. So, probably there is some interplay between many processes there, particularly planets, if there are. So yeah, we wanted to check what's the possibility to observe the VSI if you have a large planet there perturbing everything in the disk. But yeah, there is only, I think, one disk that seems to be smooth in the outer regions, but it has not been observed in really high resolution. So we expect probably as you observe in high resolution, they always start to show structures.
Okay, so thanks. If there's any question, I guess no hand anymore. So I think we can continue our discussion offline, in person. And let's thank Marcelo.
Thank you for joining. Bye.